Good afternoon. I would love to introduce our presenter today, Tomas Baca of FIU Amera, an undergrad student, presenting on miniature gas chromatograph silicon microchip in situ instrumentation. Tomas, thank you for being here. Please take it away.
Hi everyone, welcome to my presentation. I'm going to start by explaining some information and then I will answer questions in the chat afterwards. The poster you are seeing covers the basics of a project that my team and I are involved in. We're in the process of developing a miniature gas chromatograph for a handheld device implementation. We're using MEMS fabrication techniques to construct the GC because it enables technology due to its capability for component miniaturization. The functionality of such a device is outlined graphically on my poster under the Silicon UGC chip concept section. The core of a GC consists of a coiling tube-like structure with an interior stationary phase coating. This structure is what is called a GC column. It serves the purpose of capturing an inputted gas and ejecting each component in separate time intervals so they can be observed individually by a thermal conductivity detector. The mechanism by which the components are ejected in different intervals is a combination of a ramping heating element and the stationary phase. At certain temperatures, each component is released from the stationary phase and is then pushed out of the column by the carrier gas. The ultimate goal of a GC is to assist in separation of a gas. GCs are typically paired with a mass spectrometer to provide a preliminary separation step. My colleague Anna Costa is currently presenting her poster on miniature mass spectrometers. So if you are curious about that topic, I suggest you pay her virtual room a visit. This poster focuses on the miniaturization of a GC in the form of a silicon chip. The primary benefit of a miniature GC comes from the fact that GCs currently in use by forensics and other professions are typically much larger and are incorporated in non-portable desk units. Traditional GC implementations lack the capability to perform on-site chemical analysis. If you see under micro GC chip advantages for chemical separation and identification, you'll see a picture of what traditional GCs look like and what my miniature GCs or UGCs look like. The UGC chip is pretty small, smaller than like a quarter. So you can see the advantage there. Miniaturized GCs are one step to providing a well-refined handheld chemical identification tool. Under the micro GC chip MEMS fabrication section of my poster, you can see diagrams explaining how we will build the column on a chip. The front side fabrication involves first spin coating positive photoresist onto the front of a silicon wafer. Photoresist is a material that either becomes soluble or insoluble when exposed to light. In our case, we are using positive photoresist, which becomes soluble when exposed to light. A glass mask with our column pattern is then used to provide a controlled UV light exposure to the front of the wafer. This step is known as photolithography. After the photolithography, a chemical bath is applied to develop the column pattern on the wafer. The wafer can then be run through a derise cycle to etch the column cavity into the silicon. The last step of the front side fabrication involves bonding SiO2 to the front of the wafer to enclose the column. The backside fabrication is similar to the front side fabrication. The main differences involve the design outlined on the photolithography mask, the type of etching, and the thermal conductivity detector bonding. The design this time around is just feed-through holes for the inlet and outlet. The holes are anisotropically etched all the way through the white wafer to connect with the inlet and outlet ends of the column. Finally, the TCD is bonded to the outer hole. The TCD is separately batch fabricated through similar MEMS techniques.
Tomas, we do have a question just to kick things off. What is the carrier gas you plan to use?
We'll be using helium. Certain things of the project haven't been decided yet since it's in early stages of development. We kicked off actually basically this summer. a little earlier, but we're coming along.
Tomas, how large do you anticipate this final device being, seeing as the chip is so much smaller than current traditional gas chromatograph devices?
You mean the chip itself or the actual handheld device?
The handheld device, so it would be handheld,
Mm,
approximately?
I'm not too sure, but it would probably be like about the size of as that picture shows in the bottom left corner, uh, under the silicon UGC chip concept. It wouldn't be that much bigger than that. The screen would be bigger, and probably there would be a portion of it to the left or to the right where you can refresh the carrier gas, since that it eventually exhausts and you need to replace the cartridge. Um, it may have some compartment to replace the chip, because the chip degrades over time. Not super quickly, obviously. It has a good duration, but you will have to replace it at some point.
That makes sense. Or practitioners already have to replace columns in a traditional benchtop gas chromatograph machine, correct?
Yeah.
Have you run into issues in manufacturing on something so very small?
Well, we haven't started manufacturing. We're still figuring out what design we want to try, because there's many ways of implementing the column. Like, well, actually, just the pattern, on the chip, we haven't quite decided. So we're comparing different patterns. But overall, the fabrication should be pretty easy of the chip itself. I've had experience in MEMS fabrication, and it tends to go pretty simple.
We have another question. Do you expect elution times to differ due to the size of the GC?
I'm assuming so. Personally, we haven't been able to find any simulation software that would tell us more information about how this would work, so we haven't quite figured that out just yet. Mainly because the simulation software that exists is optimized for larger GCs. So all that we have right now is calculations, like analytical calculations, and what we're going to try to do is apply that to create maybe our own simulation software, so we'll be able to get more information on that.
You're really breaking new ground here, not only in development, but also evaluation, testing, and prediction then.
This is something that has been done before. We like people have. I mean, you can see in the picture there, uh, Figure 11 silicon UGC chip that people have been developing uh, GCs of a smaller size. It just hasn't been put into practice yet by the forensics or other professions.
Are you anticipating that this device would be used in the field exclusively or as a benchtop replacement in a lab?
Well, the whole point of the in a lab, probably, if there's the lab units will stay. I don't see a reason to get rid of them. In some cases, maybe the lab units will be better. But after all, this is the point of the handheld, is to be able to do analysis on the field. So if for whatever reason it's more convenient, or it's just you just need the information about the chemicals you're analyzing as soon as possible, that is what the handheld device solves. For example, in let's say you're a cop and you're analyzing a substance found on a suspect, you're going to want to know what it is in that moment. You're not going to want to have to send it to a lab and then wait for results. You want to be able to charge the person immediately.
So this would be much more accurate than some of the colorimetric field tests that are currently being used by law enforcement.
Yes, those color metrics exams, and some of them, at least from what I've heard, have proven to fail in certain scenarios. They're just straight up inaccurate. The handheld devices, such as this one, the one that I'm presenting, will be the future. They will enable cops to make sure that they get the right analysis.
We have another question from the chat. Would this be quantitative or qualitative technique? And would detection values be an issue?
So if you can see in the under the silicon UGC chip concept section, you see right there a graph output. That is what you'll get when you run it through the conductivity detector. What ends up happening is the purpose of separating the gas, well, the gas into its components, is so the detector can individually analyze each component, because the detector is non-selective. It just analyzes whatever goes through it. So when you separate the gas, it'll send it through. It'll send each component through one at a time, and you'll get this where each spike will give you will let you know which component is which, what is what. Because it on a time scale on the bottom, and the y-axis will be the thermal conductivity, which will tell you what chemical is what.
Do you anticipate this needing a physical sample, or could perhaps an air sampler be attached to this for ambient chemicals that may be floating around maybe a clandestine drugs manufacturing lab?
So from my understanding, the device, like intakes only gases. So if you want to input a gas, it could do either injection, or it could do just ambient analysis. If you want to input a solid or a liquid, you would probably use another a device prior to turn it into gaseous form and then run it through the GC with an injector.
So there would have to be an extraction step or sample prep if you had a physical substance, but
Yes.
sampling the air around a substance, this
No,
device.
it can do that. It can do that. You'd be able to. The way that we're designing it is for injection, but it is possible to make it so to analyze ambient gases.
How many different designs have you gone through on the front side and back side fabrication layouts? Do you even know?
So currently we're focusing on like a square-like shape. So what it would do is zigzag kind of. So if you see right there under, actually in figure 2, that pattern under chip-based separation channels, that's what the design we're testing right now. It's just a square and it keeps going up and down, up and down, up and down until it forms a long channel. So that's what we're testing right now through analytical calculations. We have considered other designs, but we're taking it one step at a time. We're taking care of this one first, and then we'll move on to something else if we don't like the results we get from this. So yeah, that would take care of the front side fabrication, because that's what we would fabricate on the front. As for the back side, we need to figure out how we're going to build the TCD, since that's fabricated separately. It's similar procedure. A lot of the MEMS fabrication steps are used in that, but it's not fabricated on the same wafer. It's going to be fabricated on a different wafer, then cut out and attached, bonded to the bottom of the chip.
Thank you. We have another question from the chat. Do you have any estimates as to the expected uncertainties with this instrument?
Not as of now.
Tomas, you said you had experience in this type of fabrication, the electrolyte printing. Forgive me, I am not a scientist.
It's fine. It's fun.
It seems that this sort of long loop back channel is a mathematically efficient way to create a longer channel on a much smaller substrate area.
Mm-hmm.
Was that informed by any other experience that you had in manufacturing tolerances for this small type of chip?
My experience before was fabricating a MEMS pressure sensor and some other, well, two actuators. Um, Not so much on this front, but what I did learn is the line spacing and how downscale at what a low scale you can get to, like how small the line spacings will be or could possibly be. So that's the only thing that I learned prior to jumping onto this project.
That makes sense.
Yeah.
I've seen designs for microfluidic devices, which obviously are not carrying gases but fluids, and have
Mhm.
different issues, with surface tension, etc. But do you know in length about how long this channel is when it's etched onto the chip?
Currently, we've decided on making it 3 meters, but other people do different sizes just based on how they chose to design it. As of now, we don't know whether we should scale it up or scale it down. I think scaling it down wouldn't do us any good. The longer, the better. But for now, our current designs we're looking at 3 meters.
And Tomas, just to reiterate, there was a question earlier before some other people came in. The carrier gas that you're expecting to use in this?
It's helium. Uh, it's what is typically used for the carrier gas, so we're gonna use that. And as of now, that's what we decided on. I'm pretty sure it's the best solution.
In your work on this, how have there been any roadblocks that you've been able to overcome in your time working on the project?
Roadblocks we're just that we've had is imagining how to fit all of this onto one chip, because we not just have to put the column itself is fine. That's not even the issue. It's the idea of putting the TCD on there, the what's it called? Because there's gonna need to be plumbing for it, like an injector, and as well some way of inserting the carrier gas. So that's a little troublesome to come up with. We think we have an idea on how to get it to all fit together neatly in a small chip. The size we have right now is, I believe, a little less than 1 inch by 1 inch. We're trying to go smaller, but we need to figure out how we choose to do that from here on out.
So the chip that's going to be manufactured is going to include multiple layers beyond just the channel.
Yeah, it's gonna have the on the bottom side. That's where we're gonna have to put the injectors and whatnot, because it'd be really hard to draw up just a cutoff, like a path that just cuts off at the end of the chip, and then connect stuff to that. That's much harder than just ending the path on the front side, and from the bottom side digging to, or like etching to uh the column, so that we can make the injector and such in that area.
So then this chip, as part of the larger handheld device, would almost become a easily replaceable plug and play module.
Yes, that is the goal.
It seems much more friendly for use in the field
Yeah. It's
compared to
easier.
the very, very fragile GC columns right now. I've seen the changing procedures and the maintenance required on a GC or GCMS.
We're gonna want to make these in a packaging of some sort so that you can just insert it without worrying about damaging it. Just an easy plug and play.
Tomas, you've been manufacturing these in the MEMS clean room, is that correct?
We're going to, in the Ameri lab at FIU, we're gonna fabricate these. We're gonna make several iterations to test which will be better. Once we've decided on a subset of designs that we think are gonna work best, then we'll test each of them out. We'll create them in the Ameri lab, and we'll test them individually to see which one does better in a real life situation.
Excellent. We have another question from the chat. I congratulate the team for this work. Are you planning to incorporate the chip with MS for identification of separated compounds?
You mean a mass spectrometer, yeah?
I presume that means yes, mass spectrometer.
Okay, so we don't intend on doing that just yet. We're gonna try to make it self-contained just with the UGC. Then afterwards we see what comes from it, because this is in essence a senior design project. So the scope that we have set for it is just to go as far as get a handheld UGC with a thermal conductivity detector.
Do you anticipate the handheld device having a library for identification on board, or is that likely more to be a software-based solution?
That is to the software solution, but we haven't decided whether it's just going to show a number output, just telling you what the thermal conductivity of each peak was, or we're going to have actually set a library that will be able to relate those thermal conductivities to a specific chemical. But we probably could. It wouldn't be too hard to implement.
That seems like a much smaller problem than some of your other design issues that you're tackling right now.
Yeah.
With potential applications, I can definitely see where the military and law enforcement could use this for identifying question materials. How do you see this technology being used in an industrial setting?
In an industrial setting, there's a lot of situations where there could be a leak, a gas leak, and it would go undetected because it doesn't have a recognizable smell. A lot of times, some chemicals don't, well, gases don't have a smell, but they can be very dangerous. So the point of a device like this is having something that's non-intrusive, available to uh, workers, so they can regularly check the premises to see if there's any leakage or of any sort, or there's anything in the air that's dangerous to workers.
I presume this type of device would be more sensitive than other commercially available chemical sniffers.
Yes.
And it's a confirmatory technology.
As in, sorry, I'm not entirely sure what you mean by that.
I apologize. A confirmatory technology as in uh, gas chromatography can identify a material versus something like a colorimetric test that is presumptive, where some
Yes.
changes. Okay, excellent. Tomas, what further development are you hoping to generate on this project?
From this project, I expect the UGC to be matched with a mass spectrometers to create better analysis tools, better handheld analysis tools. As I said, my colleague Anna Costa is currently doing, well, she did a presentation on miniature mass spectrometers. So the technology is getting there to the point where everything is scaling down so that it can be all implemented in one handheld device.
And do you know, is the project currently seeking any research partners for further development of components like the software or integrations or even manufacturing?
As of now, no, but we might be interested in that. We just haven't decided. If anyone is interested, you can shoot me an email. My correspondence is there at the top left under my name.
And when we publish this presentation, along with the questions and answers from the chat in written form, we will be including your contact information for anyone who has further questions after the fact, or even to get in contact with you for further development. Future plans that you'd like to communicate about this project?
In the future, we're gonna have to figure out how we're gonna implement the heating element, because this thing has to be encased in some sort of insulator so that the rest of the components don't get heated up. And so we have to fit a heating element in there and then the insulator so it can keep the electronics safe, because it's going to be near the microcontroller and a couple of other components inside the housing. So again, we don't want the heat to affect everything else. We want this to be the heat to be contained only to the UGC. It shouldn't be too hard though, because the UGC is pretty small, so heating it will be easier, as well as making a insulative compartment will be pretty easy too, I think. We just haven't come up with an idea on how to do it.
What's the operating temperature for the UGC?
As of now, we haven't decided on how the ramping will work, because different chemicals get ejected at different temperatures, and we haven't decided what chemicals we want to focus on. We can go a wide range, or we can focus on certain chemicals for our scope, which would change the ramping cycle for the heating element. Because when you start the heating, you're not going to just stick at one heat, like one temperature rather, uh, because it's not every chemical that could be in there could have does have a different temperature where they get ejected from the stationary phase. So we need to ramp at a certain rate and and have a limit where the temperature will reach.
So you may end up with chips that are designed to detect different classes of chemicals.
Yes, and since it's replaceable, the software itself doesn't have won't be affected by that at all. The chip could literally just be replaced when you're analyzing a different type of chemical or a different subset of chemicals, or a group that you are interested in at the moment. So it's the housing itself would not be at all affected. We could even have different ramping programs for what the chemicals you're analyzing. At the end of the day, we just haven't decided what those ramping programs will be like, because we haven't figured that out quite yet. So
Sure, I can see the development of different chips for different chemicals based on final delivery or user need as well. If you have industrial manufacturing that needs a certain narrow window of detection, that would be useful. Tomas, you're an undergrad at FIU, is that correct?
yep, I'm 2 semesters away from graduating.
That's fantastic. Congratulations.
Thank you.
We have another question from the chat. What is the mechanism of separation on the chip?
So the way the chip essentially works is when you inject the gas, first of all, the carrier gas pushes the sample gas into the column, and then when inside the column, it gets absorbed by the stationary phase. When you ramp up the temperature at different temperatures, certain components of the gas will be ejected, and so you eject these components in individual time intervals, or different time intervals rather, so that when they get released from the column, they come out at different times and the detector can analyze them individually.
Another question, what form of detection are you using?
As I said before, the detection is going to be a thermal conductivity detector. So it'll analyze the thermal conductivity of the chemicals, or rather the components of the gas running out of the column. and the thermal conductivity itself can be matched with the components that you're trying to identify, thus giving you a method of identification.
We are almost at the end of the poster session. Uh, Thank you so much to everyone who participated and all of your questions. They're great. We will be providing a recording of this session along with written questions and answers from the chat with our presenter's permission. I'd like to thank our presenter, Tomas Baca, for his time today. Thank you very much to everyone for stopping by. Thank you, Tomas, for your expertise in your presentation. Please enjoy the remainder of the symposium.